Okay. Just a few things about computational time. As you guys write scripts and things of that nature, it might be of interest. Now, a lot of times your computers are fast and it's not that big of a deal, okay? But it might be of interest to know how much time your computer takes to run something, okay? So here I've got, system.time, and then here I've shuffled up, 10 million integers, and I've asked this computer to sort them, okay? And it takes, and you can use this thing called system time, and it measures how long the computer takes to run this thing, okay? So, so basically, the two numbers of interest would be user and system. This elapsed time, because your computer it runs other things at the same time. So if you're like watching a video on YouTube or something at the same time as doing computations in R, your elapsed time will probably be much greater than user plus system, okay? But generally, if you're curious how much time the computer actually takes to do this, the two numbers you'll be interested in will be user plus system, okay? And then this is just simple R code. You can put in a larger R function by kind of sourcing a file or something like that. Okay. We can talk about this idea of programming efficiency. And so a lot of times what you want to do is you want to just identify kind of the most important operation in the program, and you want to count how often that thing is performed. So, if we're doing numerical integration or root finding, a lot of times we're dealing with some kind of function f, okay? And so we want to count how often do we have to evaluate that function f. If we're going to do something where we're sorting something, we want to count how many times we have to compare one value to another, x versus y, in order to do the sorting, okay? If we, when we're dealing with vectors, it's a lot easier to initialize I shouldn't say easier, but it's computationally more expensive to resize or redimension a vector than it is to create the vector and then just change values inside the vector. So you can see here I'm doing two operations that are pretty much exactly the same thing. In this one, I have the vector fully formed, okay? I've got 10,000 numbers, and I'm creating the vector x so that it is the number 0 repeated 10,000 times, okay? And then I ask R to run through this loop for 1 through 1 in 10,000, just square that value and store it. And we can see it doesn't take very much time. If I just create an empty vector using C, and basically when I run the same operation, every time R does this, it has to expand the vector. It has to grow the vector every time with each loop. And when we do that, you can see it costs more time. Now, as far as how long the computer takes to do this, it's not very big, right? With 10,000 numbers, it's not that big of a deal. And it probably takes longer to type this thing out than the difference gained here. But if you're dealing with things on the magnitude of infinity, or not infinity, a billion or things like that, hundreds of millions, sometimes it makes sense to spend the extra time to fully initialize all of your vectors. We have R can do loops, and a lot of times it's easy for us to think of loops, but vectors are generally more efficient for R. If we think of, you know, computational time, exactly what's going on, it seems like, well, the loop shouldn't take that much longer than the vectorized version. But at the base level, the way R is written, the programming language, it has to do this translation from loop form into computations and then back. And when you give R a command in vectorized form, the translation is easier for R to do. Okay, to translate from vectorized form into kind of the tasks that the computer needs to do. It's easier for R. And so R was we can compare, you know, how some of these operations compare when we have it written as loops versus when we have it written in vector form. And we can see the computational time difference is quite substantial. And so, excuse me. So what we have to deal with is that you know, it's sometimes it's worth thinking, can I write this program not with a loop but using a vector? Okay, and that's going to be I would say a pretty important skill that you develop as an R programmer. Okay, if you're going to try to do any kind of programming in R, you want to start thinking more in vectors and less in loops. Sometimes loops are unavoidable. You've got to create a loop, and that's fine. But if you can do things in vector form, it's better. And this is probably one of the big complaints that people have about R, is that it sucks at loops. Okay, trying to run loops in R is it's not computationally efficient compared to a lot of other languages, especially in languages where there's a compiler. And it looks at the loop and it goes, I recognize what I'm doing here. I can create, you know, write code in a much more efficient manner here. Whereas R, it's called an interpreted language. Sorry, R is an interpreted language, not a compiled language, and so the way it translates the code you write into stuff is very different. Okay, so here, for example, we're going to create a matrix with 1,000 rows and 1,000 columns. Okay, there's a million numbers here. Okay, and we want to create column sums. Okay, and so what we're going to do is we're going to say, you know, for each column, go through, and we're going to take the sum starting at 0, and then I want you to go through the row, each row, row by row by row, all through 1,000 rows for the first column, add that up, and then go to the next column and go, you know, go through all 1,000 rows, add those up, and so on and so forth. That's essentially what column sums are, right? If I gave you a matrix and I said create column sums, that's what you would do. You would take your calculator out and you would go through the first column, add up each number in that column, you know, from the first row to the last row. You would write that number down. Then you go to the next column and you do that. And so, you know, we can write this code exactly as what we would do, and it's fine. And we can see, you know, to add up 1,000,000 numbers in 1,000 columns, it took the computer 1 second, a full second to do it. Okay. If we ask the computer apply, we're going to use the apply function. Okay. And we're going to apply the command sum across the columns here. We can see that it took our, you know, 5/10 of a second. Okay, or I mean 5/100 of a second. Okay, so this, just switching from this thing into this, it's a lot faster. If we create a something like this, where basically we've created a loop for each column, but within the loop we just said take the sum, reduce big matrix, just pull out column I and take the sum of that column. This is a vectorized operation, and do that for all 1,000 rows. It takes even less time. Okay, and then lastly, there is something just called column sums, and this is a vectorized operation of adding up the column sums, and R can't even. It says it takes 0 time. No, that's not true. It took a finite amount of time, but it's a very small amount of time. Okay, and so I could grow this and do like 100 million rows, 100 million values, or something like that, and we could see that all of these things would be on the order of 10 to 100 times larger. Okay. It is worth noting or talking about memory. Okay. We a lot of times try to vectorize our operations, and when we do that, it stores all of these values in memory. Okay, and most likely you're not going to run into a problem with memory, right? Your computer probably has what, 2 gigabytes, 4 gigabytes, or 8 gigabytes of RAM or something like that. You probably won't run into issues with memory, but you could if you're dealing with a giant data set, on the order of several gigabytes in size. You could start to run into memory issues, and so you might have to start chunking out your operations into smaller pieces. Okay, because as soon as you start writing to your hard drive in order to keep track of these things, it R reduces to a crawl. Okay, and I wouldn't say crawl, but the operations take much longer. Okay, but next year when I talk about this, this issue of memory becomes less and less of a deal. Well, I guess it's still an issue, because as much as our computers get faster and bigger and more capable, our data sets keep growing as well. So we might always be running into this problem. But as far as things we look at in our course versus maybe in a industrial setting, we might not run into this issue. Okay, so these are just kind of like computational issues that we have to think about when dealing with as we enter this world of computational statistics or numerical methods. Okay. All right, so I'm going to kind of one of our first topics under numerical methods is root finding. Okay, let me. Okay, and I'm. These are slides that accompanied our textbook, chapter 8 on root finding, or I'm sorry, chapter 10 on root finding. And so root finding is kind of this age-old problem of you have some kind of function, and you want to know where that function crosses the value 0. Okay, and so if you can graph the function, it's very easy. You just say, oh, it crosses the line 0 right here and right here. Okay, but if you if you're just given a function and you don't know, it takes a lot of computational power to graph a function. Okay, because you got to specify a range, and then you have to calculate maybe 1,000 values along that range, and you have to calculate the function for all 1,000 of those values, and then you'd look and see where it crosses 0. A lot of problems can be reduced to finding roots of a function. So we can use root finding as a way for minimizing a problem and things like that. So later on we'll talk about optimization, okay? And if you think back to calculus, one way to find a maximum or a minimum of a function, so if we want to find the maximum or minimum of a function in calculus, one way to do this is to take the derivative and find where the derivative is equal to 0, okay? And so that is an application where root finding where the function is equal to 0 is very important, okay? So and we'll explore this topic later. If we're looking for a so the ordinary least squares is already a solved problem, right? We know, you guys are familiar with least squares regression, right? No? Okay, so in least squares regression, how are we choosing our regression line? Let me. Okay, so if I were to create a if I were to create a data set like this, okay, and something like this, how do we decide which line is the best fit line? This is terrible. What's going on here? Okay. What is the criteria for deciding what line is the line of best fit?
It's the one where the sum of the squares.
Yeah, we're trying to minimize the sum of squares residuals, right? So we look at. Let me pull this up. I got to look up visually explained regression. Here we go. Explain visually. This will be better. Okay, so if we've got this data point, what we're trying to do is, I can change where the regression line is, okay, and we can see the vertical distance between the line and the dot. This is called the residual, and we can square that, and we can look at the total sum of the squares here, okay. And so by finding the least squares line, we're trying to find the spot that minimizes the total sum of squares here, okay. And that's basically, so that's an optimization problem, okay. Finding the best fit line is basically trying to find the equation that minimizes the squares of the residuals. So if you have an optimization problem, one way to solve it is you find the function that you're trying to minimize, then you take the derivative of that function, and then you try to find where that derivative is equal to 0, okay? So anyway, this is why we bother with root finding here, okay? So you have some function, you want to find out where it's equal to 0, okay? So one method is called fixed point iteration, and we've got some slides here, and it's explained in the book. I think this video on YouTube does a pretty good job of explaining fixed point iteration. So I'm going to go ahead and just defer to this video here, okay? So we're going to try to find roots with fixed point iteration, okay? Is audio coming through the... That's only on my machine, huh? Let me see. Let's try this.
Use another approach to finding roots called fixed point iteration. How does fixed point iteration work? First, if we're given f of x, we'll set it to 0, and then write it so that way we have x is equal to something. Then we'll label the left side as x sub n plus 1, and the right side with x sub n. Then we'll go ahead and take an x1 and plug it into our equation, and repeat it with every new x until it converges.
So again, so I'm going to pause right here. We have some f of x, okay, and we want to set it equal to 0, okay? And so we're going to write x in terms of x equal to something. So we label, what we're going to do is we're going to label the left side as using xn plus 1 and the right side using x of n. And we're going to use this as a way to iterate between one value of x to the next value of x. So it's like x at time n, and then the next iteration, x at n plus 1, is going to be something else, okay? All right, so...
Given an example of where we want to find where x squared minus x minus 1 is equal to 0, here's how we'll do it. So, using fixed point iteration, we'll set x in terms of something. And there's a few ways to do that. One way is to say that x squared is equal to x plus 1, and therefore x is equal to 1 plus 1 over x. So x sub n plus 1 is equal to 1 plus 1 over x sub n.
Okay, so again, you know, this is our function. We set it equal to 0, and then we set x equal to x on the other side, basically. So we've just solved x for itself, and then we say the one on the right is x of n, and the one on the left is the next iteration, x of n plus 1.
We can also say this, that x squared minus x is equal to 1. Therefore, if we factor out an x and we divide by that, we can say x is equal to 1 over x minus 1, and label it accordingly. Here's another approach that looks like a good idea, but turns out not to be, because we set x equal to plus or minus the square root of x plus 1, which gives us two answers for x sub n plus 1, which is not a good way to go. So we'll go ahead and evaluate both of these. First, the left side. We'll go ahead and pick x sub 1 to be a value of 2. Plug that into our equation to find x2, which turns out to be 1.5. Plug x2 into our equation to find x3, and so on and so forth. It looks that these values seem to be converging on the value 1.618.
Okay, so all we do is we just pick some arbitrary value, okay? Well, not arbitrary. Well, hopefully a value that's near the root, and then we just run through a series of iterations saying the next value that we get is the one based on, you know, we say the next value is going to be this, and then we take that value and we plug it in and keep going.
On our other equation, let's go ahead and start closer to the root. We'll pick x1 equal to 1.6, and it should converge that much faster. Plug in x1 to find x2, x2 to find x3, and so on. Although it looks like our values are growing rather than shrinking, and indeed, this does not converge. So why is it the left equation converged and not the right one? When does convergence occur? Remember that we set xn plus 1 equal to something? We'll go ahead and call that something g of x. So if we do some fancy math, we come up to the conclusion that if g prime at the root is less than 1, the function will converge.
Okay, so I mean, he just kind of flies through this, but this is kind of the important part here. If you take the derivative at that root, okay, the absolute value of the derivative at that root, if that's less than 1, it will converge, and if it's not, then it won't.
This is basically saying that the error after every iteration is getting smaller, which we would expect in a converging function. So now let's examine our two equations that we had earlier. With our first equation, we'll go ahead and call that g of x. And if we take the derivative of g of x, we can get g prime. Plug in the root for that value, and we get negative 0.31, etc., which turns out to be less than 1 in absolute value. Therefore, this one converges. On our other side, we'll go ahead and also call that g of x, find our g prime of x, and plug in our root, which equates to about negative 2.618, greater than 1 in absolute value. Therefore, this one does not converge. Now, about the order of fixed point iteration, it really does depend on the function you start with. You remember that we said x of n plus 1 is equal to g of x, and how that if g prime at the root is less than 1, we said it will converge. If g prime at the root is exactly equal to 0, however, the function converges quadratically, at least. And if you take the derivative of g prime to find g double prime, if that is also equal to 0 at r, then the function will converge with order 3, and the pattern continues. So if g triple prime at r is also equal to 0, then it will converge of order 4, and so on and so forth. Please also note that Newton's method is actually a special case of fixed point iteration.
Okay, we can watch the Newton's method. This guy makes good videos. Okay, so I don't know if I want to go through all of these slides here. So yeah, these were slides that accompanied our textbook, and so the words here are almost directly from the textbook, chapter 10. But so basically, you know, we have this issue where we are setting g of x equal to x here, okay? And so, you know, here we have this line of x equal to x here, and we can see, you know, when we take a value and we compute where it would equal, it starts to diverge here. Okay, whereas over here we can start over here, and then we take the value and it converges to a point here. Okay, so we have this issue of convergence and divergence, but it is one way for us to solve kind of these things. And so if we have this function here, we can you know, there are a few different ways for us to solve for what you know, just like in the video, there are a few ways to express how x would be. We can express x in different terms, and we can run the corresponding script. Okay, and so let me pull up the script for fixed point iteration here. Take this. All right, I'm having issues opening my. Okay, so here we are. Okay. So fixed point, it's a function, okay, and it takes in a few arguments. One is the function of x. So this is kind of our g of x equal to x. All right. So this is the function that we provide it. We give it an initial starting point, and then it will keep running until the difference between one iteration and the next iteration is smaller than our tolerance, or it reaches a maximum number of iterations. And this is important to have the max number of iterations, otherwise in a diverging thing it will just keep going, right? And so so what we do is we just take our initial value of x and we set that to x old, okay? And then we calculate the function at that point, okay? Basically at this point it's just the initial point, okay, and that's going to be our new iteration, new value of x, okay, and that's iteration 1, okay. And then what we do is we just loop through it, okay, and basically if we take just keep doing this as long as you know, the difference is greater than our tolerance, or as long as our iterations is less than the maximum number of iterations, okay. And then each loop we do the same thing. We just take our new value, we set it to what our quote old value is, and then we calculate the function at the new location, or now it's the old location, and we set the value of the function equal to x new, okay. And so we're just, again, the illustration is that you've got the line x equal to x, which is the straight line, and you're kind of comparing, you know, what is the function at that new value. Okay, and then just iterate. and then that's it. Okay, and so we can run through this. So I'm going to create a function called fixed point. So we have a fixed point function, and then we'll try it. Okay, so we're going to define our function of x. We're going to set x equal to if we take the exponent of both sides, so basically what we've done here is we set this equal to 0, and then I added the exponent to both sides, right? And then I took the exponent of both sides of the equation. So exponent of log x is just x, and on the right hand side I got exponent of exponent negative x. Okay, so I'm going to just set this as a function here. This is going to be function 1. Okay, and then we can just see, function 1 of 3 or some, ftn1 is something like that. Okay, and then so we can run the fixed point iteration starting at the initial value 2. And when I do that, we can see it converges after 14 iterations. And then, or you could express the function again. What we could do is we set f of x equal to 0. All right, and we got 0 is equal to log x minus exponent of negative x, and then all I did was I added x to both sides of the equation, and so I got x is equal to, I guess we just subtracted this from x on both sides, okay, and then so we got, I could add it to both sides, or I could subtract it from both sides, right? If I set this thing equal to 0, and then I say, x is equal to this, add x to both sides, I would get this. And if I set it equal to 0, but then, and I'm, add x to both sides, but then I subtract this on the other side, we get this. So we can express the x in terms of itself in different ways here. And then, and so if I use function 2, which is g of x is equal to x minus log x plus the exponent of negative x, I've got that, okay? And we can just run the same calculation here using function 2 in a tolerance, and here it converges after 6 iterations, okay? So just whatever function we have, it can affect what we have, okay? And then function 3 is basically x plus log x minus that, and I can run it after 3 iterations, and here it failed to converge after function 3. So this is fixed point iteration. This is one way to solve for roots of an equation. Okay, with the Newton-Raphson method, okay, this is it's a generalization of the Newton's method, but we'll watch the video for
special case of fixed. Hello Internet, Oscar Release here, showing you how to find roots using Newton's method. And Newton's method is a really neat algorithm that's a lot popular.
Let's plug in our sound again. So we'll watch it for Newton. This is similar to Newton-Raphson, except Newton-Raphson allows for other forms here. Okay, but we'll.
This is in bisection, and it's pretty simple too. So let's get started. First off, what is Newton's method? Well, Newton's method says to first pick an x that's close to the root of a function, and then also take the derivative of the function to get f prime, and then plug it into this formula. of xn plus 1 is equal to xn minus the function at xn divided by f prime of xn. And please make sure that f prime of xn is not 0, so you don't get a divide by 0 error. Afterwards, you're going to repeat until it converges, where xn is about the same as xn plus 1. Here's a...
Okay, so again, as far as what we do is we just say the next location that we're going to use. So we have an initial value of x, or just our kind of our current value of x, and the next location that we're going to do is going to be, we're going to just subtract off this number. And we're hoping that subtracting off this number brings us closer to the converged point of the root, okay? And that number that we're subtracting off is the ratio between the current value and the derivative at that current value. And it might be like, well, how is this going to work? But we'll look at the picture and we can see what's going on here.
Good example and a graphical representation. So say you want to find the root of the function sine of cosine of e to the x. When you have your function, you'll first pick an x. So let's pick this x and call it x1. And you're going to find the derivative of that point to get the slope. And what it's really giving you is a tangent line of this function at x1. And then you're going to use that line to find your next x.
So by taking the kind of the ratio between the slope and the value here, you end up getting this point over here, because it's because if you think of what the slope is, right? So the tangent line, this is so when you take the derivative, you're getting the slope, right? And so if you do, the slope is rise over run. And what we're doing here is we're basically doing rise divided by the slope. And so that's going to give us the value of run. And that's why we end up over here. Okay, so whenever you take x1 minus the ratio between the height and the slope, okay, so if you think of what the slope is, which is, quote, the rise divided by the run, and now I'm doing the value divided by the slope, okay, I'm going to get the run, okay, because I've got rise divided by rise over run. So I've got rise divided, that's going to turn into the run. And so that's why I'm getting this point over here. Does that make sense? Okay, so that's what we're doing.
Which we'll call x2. And we'll repeat this process until we come up with a root. So now if we take the derivative of the function at x2, we're going to get another tangent line. And this time, where that intersects is close to the root, and we'll keep going until we find something that's acceptable and the function converges. Please note, though, that your point really should be relatively close to the root that you want to find. However, if the point that you get has a slope of 0, then you'll never know where to calculate your next x. Now let's say we want to find a square root using Newton's method. Well, first we're going to use this function of x squared.
I mean, this is good enough. You can watch the full video on your own time. Okay, so that's Newton's method. I guess that's essentially what we have going on here. Okay, we're just taking the difference between. We just take we say the next value is going to be our current value minus the ratio between the height and the slope, which is basically this is going to be give us the location of where the quote run crosses the line, and we saw that the diagram of how it works. And so here it goes. Okay, and so here's all of this proof for how it works. Let's look at how we can code this. Why is this not? And I'll okay, and then so when we write the function for Newton-Raphson, it returns the function and the derivative. Okay, so this is kind of the key part here, is that when we're writing the function, we need to return the function and its derivative, which feels like, oh, maybe you know, what do we have here? Okay, so we've got so here's our function, log x minus the exponent at negative x. Okay, and then the derivative of this is going to be this, and we're going to calculate both of these. We've got, so when we run this function, it's going to return both the value of the function. So if I say ftn for let's say the value 10, okay, it's going to calculate the value of the function itself and also the derivative of the function at that point. Okay, so let's we're going to have an initial starting point of 2. Okay, let's look at what Newton-Raphson does. Okay, so again, the way we have the function programmed is that it returns the value at of the function as f of x1, and then the derivative as f of x2. Okay, and so all we're going to do is we're going to just say, take our current value of x, subtract off this to get our new value of x. So we're subtracting off the size of the quote run there, and then we're going to just calculate f of x again, and iterate over and over and over again. So this is where the work is done here. Okay, and the computation is spent using calculating the value of x and its derivative. Okay, so this requires that we do some math calculations where you got to figure out how you can write the derivative in the form of a function here also. Okay, so all right, so we'll run this. So what is this called? We called it Newton-Raphson. Newton-Raphson function 4. Okay, where function 4 returns both the value of x and its derivative. Okay, and then it converged very quickly after four iterations here. Okay. The bisection method. Okay. Do we have the video for bisection method? Okay, so the bisection method. Let's see. Where's this guy's video on bisection method? Basically, for the bisection method, you just know that the function crosses some interval at crosses the line 0 at some interval. Okay, within some interval, because basically you calculate to the endpoints, and if you get a negative value on one side and a positive value on the other side, okay, you know that the function has to cross the line 0. If it's a continuous function and you get if the function at x equal to 1 is negative and the function at x equal to 10 is positive, then you know that somewhere between x equal to 1 and x equal to 10, you've crossed the line 0. Okay, if you've got a negative on one side and a positive on the other side, you know it crossed 0. So you just start where you've got x on the left side is less than x on the right side, and then if the product of those is less than 0, meaning one is positive and one's negative, you know that it has crossed. Okay, so you just check to see if the difference between left and the right is less than some epsilon. Okay, and if it is, then you stop. Okay, otherwise, find the average between the left and the right. So find the midpoint here. This is going to be the where you are bisecting it. Okay, so you so let me just, maybe I can draw another picture here. But I'm having trouble here. Okay, so let's say you've got some function here, okay, and we're going to say that you know, this is the line 0, okay? And you start here and here. So this will be x on the left, and this will be x on the right, okay? And then so you take the halfway point between here and here, okay? And this, I forget what we labeled that. That's called xm, x the midpoint, okay? And basically you're going to calculate the value of the function right here, okay? And then you say, okay, well, x left and x midpoint, these two are both negative, so if I multiply those two together, I'm over 0. Whereas over here, x at the left and x at the right, one is negative and one is positive. So this is now going to become my new xl. And then I calculate the halfway point right here. And then I say, oh, here this is positive and this is positive, so I don't want to pick that side. This is negative and this is positive, so this is gonna become my new x on the right. And then you just keep going back and forth. You find the midpoint, and that's the bisection method. Okay. So you just say if the left and the midpoint is less than 0, then you're going to set the right xr to equal the midpoint. Okay. And if this is not less than 0, then that means the new left-hand point will be the midpoint. And then you just keep repeating. Okay, and that's the bisection method. And so the bisection method requires us to calculate the midpoint, evaluate the function at the midpoint, and then loop through that. All right, so I'll post all the code up for the bisection, and I'll post up these notes as well. Okay, so let's just look at the bisection method. It requires a function that it's going to return a single value, okay? And we give it the left side, we give it the right side, and then all we do is, okay, we give it an error if the left is not bigger than the right. I mean, if the left is bigger than the right. Okay, so we just calculate the function at the left side. We calculate the value of the function at the right side. And, okay, if the left is equal to 0, then that's the root. And if the right is equal to 0, then that's the root. Otherwise, we're going to see if the function at the left times the function at the right is what is this? If that's greater than 0, okay? And if that's the case, then we've got a problem where it doesn't cross 0, okay? All right, and this is where the actual algorithm works, okay? So if the difference between these two things is greater than our tolerance, so we keep going, okay? What we do is we find the midpoint, we find the function at the value of the midpoint, okay? And if the midpoint happens to be 0, then great, okay? Otherwise, if the left and the midpoint are less than 0, times if the function at the left and the function at the midpoint is less than 0, then that means the function crosses 0 on the left-hand side of the midpoint, okay? And so that means we're going to assign the new right-hand side of our interval to be the midpoint, okay? And then we can say the function at the right-hand side is the function at the midpoint. See, by doing this, we avoid having to do recalculations, okay? By rather than saying, okay, now that I figured this out, I want to recalculate the function at the right, I can just say, okay, just use this. You've already calculated these values, so store them, okay? So each time we only have to calculate the function one more time, okay? Because you don't want to have to say, oh, well, this is the new right-hand side, so calculate the function at the right-hand side. We're saying, oh, we've already done that calculation, and do it, okay? And if the left times the midpoint, if the value of the function is not less than 0, then that means the function must have crossed the line 0 on the right-hand side of the midway point, okay? And then so we assign the left-hand side of our boundary here, and then we just keep running through the mid loop again. We just say, okay, calculate a new midpoint, calculate the function at that midpoint, and then decide whether you want to keep the left-hand side or the right-hand side, over and over. So there's just a few. Here, the calculations involve calculating the value of the function at the midpoints, and then doing a comparison to see if whether we want to keep the left-hand side or the right-hand side. And so this is the bisection method. Okay, and so we can use this function. It's the same function, log x minus exponent of negative x. This is function 5 here. And then we can do a bisection method. For this stuff right here. Okay, so it took us 20 iterations, because every time, so we started off at 1 and 2, okay? So at 1 and 2, the midpoint was 1.5, and we said, okay, the root is in between 1 and 1.5. And then we calculate the midpoint there, and we got 1.25 and 1.5, and we said, okay, well, it has to be between there and there. And we keep going back and forth, and each time we're just getting halfway, and we're getting closer and closer and closer, and we finally say it's converged right here. And that's our solution there. Okay, so I'll post up all the code. Go ahead and encourage you guys to kind of study the code. This is the root finding, which is one of the kind of basic methods in numerical methods, but it's an important one. Okay.